Welcome to Deep Dive with Emily and Phil. Today you're going to be diving into the world of probability distributions.
Oh, cool.
Specifically, how to figure out what a distribution looks like just by analyzing the data.
It's like being a statistical detective.
Right.
You're using clues to uncover the hidden structure of the data.
Yeah, I love that analogy. We've got some lecture notes and slides to guide us.
That's good.
And I'm really curious about this idea of finding the parameters of a distribution.
Mm-hmm.
What exactly are those?
Well, think of parameters as the DNA of a distribution. They're the specific values that define its unique shape and characteristics.
Gotcha. So different distributions have different parameters.
Exactly. Take the familiar bell curve of the normal distribution.
Right.
Its parameters are the mean, which tells you the center, and the variance, which tells you how spread out it is.
Okay.
If you know those two values, you know everything you need to about that specific normal distribution.
So if we're trying to figure out the distribution of some data, we need to find those key parameters.
Right.
Okay.
Sometimes it's straightforward, like calculating the mean and variance for a normal distribution.
Sure.
But for more complex distributions, things get trickier.
That's where this maximum likelihood estimation, or MLE, comes in, right?
Yes.
I've heard that term before, but I'm a little fuzzy on how it actually works.
MLE is a brilliant method for finding those elusive parameters, especially when dealing with more complex scenarios.
What?
Imagine you have a bag of marbles, and you know there are red and blue marbles, but you don't know the exact proportion of each.
Okay, I'm picturing it.
Right.
So we've got our mystery bag of marbles, and we want to figure out the most likely ratio of red to blue.
Exactly. So you start taking samples of marbles from the bag.
Okay.
Let's say you pull out 5 marbles and they're all red.
Okay.
What would you guess about the proportion of red marbles in the bag?
Well, based on that sample, I'd guess there's a high probability of there being a lot more red marbles than blue ones.
That's right. And that intuition is at the heart of MLE.
Okay.
It's all about finding the parameters that make the observed data the most likely.
Gotcha.
In the case of our marbles, we'd adjust our assumed ratio of red to blue until it maximized the probability of observing 5 red marbles in a row.
So we're tweaking those parameters until they fit the observed data like a glove.
Precisely. Now think of this likelihood as a mathematical landscape with peaks and valleys.
Okay.
Each point on that landscape represents a different combination of parameters, and the height of the point represents how likely it is to observe our data given those parameters.
So a high peak means those parameters make our observed data very likely.
Yes.
While a low valley means those parameters make our data unlikely.
You got it. MLE is like a climber searching for the highest peak on that likelihood landscape.
Okay.
They keep adjusting the parameters moving uphill until they reach the summit, the point that maximizes the likelihood of observing our data.
That's a really helpful visualization. So MLE helps us find the parameters that make the data we see the most probable, even if we don't know the exact distribution beforehand.
Absolutely. It's a powerful tool for uncovering those hidden parameters and understanding the underlying structure of our data.
Okay.
But sometimes we might not even have a clue about what kind of distribution our data follows.
Right.
That's where kernel density estimation, or KDE, comes in.
Right. I remember Professor Wu mentioning KDE.
Yeah.
Sounds a bit of a statistical wild card.
Yeah.
You can handle data that doesn't fit neatly into those standard distributions.
Exactly. KDE is a brilliant technique for approximating the probability density function of data without making any assumptions about its underlying distribution. Think of it like this. Imagine you have a bunch of fireflies scattered randomly in a field at night.
Okay, I can picture that. A field full of twinkling fireflies.
Now imagine each firefly has a little glow around it, like a miniature spotlight. With KDE, we're essentially placing a tiny Gaussian curve, or kernel, centered on each data point.
Okay.
Similar to those firefly glows.
So each data point gets its own little bell curve.
Precisely. And these curves overlap and blend together, creating a smooth, continuous curve that represents the overall distribution of the data.
It's like we're using those overlapping glows to illuminate the shape of the data in the dark.
That's a great way to think about it. The more data points we have in a particular area, the brighter the combined glow, resulting in a higher peak on the KDE curve.
And what about those individual Gaussian curves? Does their width matter?
Absolutely. The width of those Gaussian kernels, controlled by a parameter called the bandwidth, determines how smooth or bumpy the resulting KDE curve will be.
Okay.
A smaller bandwidth results in narrower kernels, which can highlight fine details but might also make the curve too jagged.
Right.
A larger bandwidth creates wider kernels, leading to a smoother curve that might obscure some finer details.
So it's like adjusting the focus on a camera lens. We want to find the right balance between clarity and smoothness to capture the true essence of the data's distribution.
Exactly. KDE is a powerful tool for visualizing and understanding the shape of data, especially when we don't have any preconceived notions about what that shape might be. It really is. And you know what's fascinating about KDE is that it doesn't just give us a pretty picture, it actually allows us to estimate probabilities.
Oh, that's interesting. How does that work?
Well, remember that the area under a probability density function always equals 1, representing the total probability of all possible outcomes.
Right. I remember that from stats class.
Yeah.
But how do we calculate areas under a curve that's created by all those overlapping Gaussian kernels?
That's where the magic of calculus comes in. We can use integration to calculate the area under any portion of the KDE curve.
Ah, calculus. That brings back memories.
Right.
Not all of them good, to be honest.
Sure.
But I trust you when you say it works.
Well, you don't need to be a calculus whiz to appreciate the power of KDE. The key takeaway is that it gives us a way to estimate the probability of observing a data point within a specific range.
So if we're looking at the KDE curve for, say, the heights of people in a population, we could use it to estimate the probability of finding someone between 5'8" and 5'10".
Exactly. And that ability to estimate probabilities is incredibly valuable in all sorts of fields.
Okay.
But, before we get too carried away with KDE, I think it's worth circling back to MLE for a moment.
Okay.
We talked about it conceptually, but I want to dig a little deeper into why it works so well.
I'm all ears. I'm still trying to wrap my head around this idea of maximizing the likelihood of the data.
Well, let's go back to our bag of marbles example.
Okay.
Remember we said that if you drew 5 red marbles in a row, you'd intuitively guess there's probably a high proportion of red marbles in the bag.
Right, because it would be pretty unlikely to get 5 reds in a row if the bag was mostly blue marbles.
Exactly. And that intuition is based on this idea of joint probability.
Okay.
It's the probability of observing all those events together. In this case, drawing 5 red marbles consecutively.
Okay, so joint probability is about the likelihood of a whole sequence of events happening.
Precisely. And MLE is all about finding the parameters that maximize that joint probability, making the observed data the most likely outcome.
So we're tweaking those parameters until we find the combination that makes our sequence of 5 red marbles the most probable.
Exactly. And here's the key point. The parameters that maximize the joint probability of our sample are also the most likely parameters for the entire population of marbles in the bag.
Ah, so by finding the parameters that best explain our sample, we're also finding the most likely parameters for the whole bag. It's like we're extrapolating from our small sample to the larger population.
Exactly. And that's why MLE is such a powerful tool for inference.
Okay.
It allows us to draw conclusions about a population based on a relatively small sample of data.
That makes a lot of sense. But I'm curious, how do we actually go about finding those parameters that maximize the joint probability? It seems like a bit of a mathematical treasure hunt.
Well, there are different approaches, but one common method is to use calculus. We take the derivative of the joint probability function with respect to each parameter and set those derivatives equal to 0.
Okay, calculus again. I'm starting to sense a theme here.
Don't worry, you don't need to solve those equations yourself.
Right.
The important point is that by setting those derivatives equal to 0, we're finding the points on that likelihood landscape where the slope is 0.
Okay.
Those are the peaks and valleys we talked about earlier.
So we're essentially looking for the highest peak on that landscape, which represents the parameters that maximize the joint probability of our data.
But exactly. And that peak represents the most likely explanation for the data we've observed.
This is all starting to click into place now. We've gone from simple distributions with easily calculated parameters to this idea of using MLE to find the parameters for more complex scenarios.
Yes.
And then we have KDE as a powerful tool when we don't even know what kind of distribution we're dealing with.
You've got it. It's like we've assembled a whole toolkit for exploring and understanding the hidden structure of data.
I'm really enjoying this deep dive. It feels like we're peeling back the layers of statistical mystery and uncovering the underlying patterns that shape our world.
Yeah, it really is. And the more tools we have in our toolkit, the more effectively we can analyze and interpret data no matter where it comes from.
I'm curious, going back to parameters for a moment.
Okay.
Professor Wu gave this interesting example in his notes. He said that if you know the average lifespan of a certain type of light bulb, you can use that information to figure out the parameters of an exponential distribution.
Oh, that's a classic example of how understanding parameters helps us model real-world phenomena. The exponential distribution is often used to describe things like lifespans or waiting times.
Right.
And in that case, the key parameter is directly related to the average value.
So if we know the average lifespan of those light bulbs, we can essentially plug that value into a formula, and boom, we have the parameters for the whole distribution.
Pretty much. And once you have those parameters,
Right.
you've unlocked the equation that describes the entire probability density function for that distribution.
That's amazing. It feels like we've come full circle from trying to figure out the shape of a distribution to using parameters to pinpoint the exact equation that describes it.
Exactly. And that equation then allows us to calculate all sorts of things, like the probability of a light bulb lasting a certain amount of time, or the likelihood of having to replace a bulb within a given time frame.
So parameters are really the key to unlocking a whole world of insights about a distribution. We've covered a lot of ground today, from basic distributions to more complex methods like MLE and KDE.
We have, and each of these approaches helps us gain a deeper understanding of how data is structured and how we can use that knowledge to make more informed decisions.
Well, this deep dive has definitely given me a new appreciation for the power of statistical analysis. It's not just about crunching numbers. It's about uncovering the hidden stories that data can tell us. Well, that's all the time we have for today. But I hope you'll join us next time as we continue to explore the fascinating world of statistics.